Hello, everyone. Hello, hello. Welcome to another Jakarta Tech Talks. We have today Sebastian Daschner here with us, and apologies to everyone for a little bit of a delay here. It is the technology, of course, that caused the problems, so it's not us, never us. So I'll just right away hand it over to Sebastian and give him a chance to get going with the Kubernetes and Istio for Jakarta EE developers. Thanks, Sebastian, for joining, and take it over.
All right. Yeah, thanks a lot for the introduction, and hi from my side. My name is Sebastian Daschner, and welcome to this talk, Kubernetes and Istio for Jakarta EE developers. So about myself, I'm Sebastian Daschner, born and raised in Munich, Germany, and I am a developer advocate for IBM, and I have a big Java background and enterprise software background in general. And today I want to show you a few things on why we Java EE or Jakarta EE developers should be interested in cloud native technologies, specifically Kubernetes and Istio, and what that is. So we're going to see a little bit about that. And first of all, I want to introduce an example microservice, quote unquote, example application, or actually two applications, because one application is boring and we want to have some communication, specifically with container orchestration and service meshes and all that. And I like coffee, so I'm going to have an enterprise Java and enterprise coffee example. So what that is, we're going to have a coffee shop example of enterprise coffee with two applications, two microservices, if you want. One is called coffee shop and the other one is called barista. So that means if we want to order some coffee as a developer, we go to the coffee shop as a client and make some coffee order. And then for the sake of the example, we have a synchronous communication from the coffee shop to the barista backend. So it works a little bit like this. We have a request coming in, order coffee. That could be an HTTP endpoint or whatever boundary we offer. And that then does a synchronous request to the barista backend. So we're going to have order coffee and then something like start the coffee brewing process and order that at the barista backend system. Okay, so finally, let's go to the code. Enough slides. So what I have is actually two enterprise applications that use the Java EE APIs or Jakarta EE APIs as in the future. And also MicroProfile. I'm going to show a little bit of that in a second. So one is called Coffee Shop and the other one is called Barista. So these are Java Enterprise projects. We're going to have the Java EE 8 API that is provided. A little bit more about that in a second. And just because I'm brave, I use JDK 11 already on an application server. I use OpenLiberty. And let me quickly have some quick walkthrough to the code, and then we're going to deploy that. So today it's a little bit less about only Java EE or Jakarta EE APIs. It's a lot more about the cloud native environment. So we're quickly going to deploy that using Docker containers and, of course, Kubernetes clusters and Istio service meshes. So how that works, this order coffee process is, let's have a look at, there is one resource that is called orders. So our order coffee boundary is going to be an HTTP endpoint that we implement using JAX-RS. So as enterprise developers, we're probably familiar with JAX-RS. So we have something like add path orders annotation on a class that makes us that gives us a JAX-RS resource here. And then we have something like give us the orders in application JSON format, and also take some order some coffee, where we can provide a plain a Java object, a type, a Java class coffee order. So that means we're gonna post a specific JSON object that represents a coffee order here. And then let's quickly walk through this code. We're gonna have a coffee shop order coffee. component here. Another class where we have the business logic of ordering a coffee. So if we have a look at the diagram, ultimately we want to call that second system. We're going to have a synchronous request to the barista system. That means we're going to have some client call. That might be HTTP in that case as well. This is what I have in another component that is called Barista. That is actually an HTTP client. And in my case, I use JAX-RS on the client side to connect to that backend as well. All right, and then this means, we're going to create a request here, and we're going to use the JAX-RS client API to, make an HTTP put request to the other resource. All right, that's enough for the code level on the Java EE APIs. Now, if we want to run that example in a cloud-native setting, first of all, what we might have is, we want to run that in a Docker container. So that means we need a Docker image. That means we need some Docker files, for example. So this is the Docker file for our coffee shop application. And in Jakarta EE, that is actually very simple to do, because if we use thin deployment artifacts, most of what we need is actually done in our base image. So we can provide many images and create images like how we want them. I use an image that contains the Observability application server plus JDK 11 plus some extra stuff that I will show in a second. Then we will add some thin configuration. Also show more of that in a second. And then actually the only thing we're really adding during development is the WAR file, is our deployment artifact, our coffee shop WAR. That resides inside Target if we build that using Maven, and that's pretty much it. So let's quickly demo that. We're going to have Maven to build our project, Maven clean package, and then we're going to have something like a Docker build to build our image in a specific tag. And that builds it. And also, again, this is actually super fast because we're only using caches for the base image layers, thanks to the copy on write file system of Docker. And then we have a thin deployment artifact that is actually tiny if we use that approach with only provided dependencies. So that's 20 kilobyte. And then we build this, and then we're done. All right. The same is actually true for the Barista system. So the Barista, that's even more simple. What I'm going to do here, and I'm going to talk a little bit about that later. I use only MicroProfile dependencies. That means in this case, I actually only use JAX-RS and CDI and I think JSON-P for that example for the Barista. So it's even sufficient to use that dependency. Anyway, if I use an application server that also supports MicroProfile or combinations of the APIs, depending what you need in your project, that is possible as well. So this Docker file here for our Barista application looks very similar. We have, our deployment artifact, barista.war, and the same thing here as well. All right, that's enough of Docker. Assume we know about that already. So let's go into the Kubernetes world a little bit. So if we build that, what I just showed you, we could deploy that locally, but that's kind of boring actually, because we want to run this in a cloud native setting in a Kubernetes cluster. So we could run our Docker containers, but now, I want to have an approach where I manage some containers. And this is actually where Kubernetes comes into play. Why Kubernetes? Well, Kubernetes is so-called container orchestration. Well, that means it orchestrates containers, as easy as it sounds. So that means if we have a production setting or a more sophisticated environment where we have multiple nodes actually, and not just one running laptop or something, then it becomes quite complex quite easily how to, run all of that in production, right? We need to manage networks, we need to set up ports and forward them, and so on and so forth. We need to orchestrate where our individual containers actually run, and so on and so forth. So this is actually already provided by the technology in a somewhat production-ready way. And that means we can, deploy that. So how do we get a Kubernetes cluster? There are many, many ways how to do that. For example, we could set up a mini kube on our running laptop, or we could go to the cloud for a managed environment. I use the IBM cloud that is called IKS for managed Kubernetes. And this is what I'm going to use here. So we have the kube control command line available for, well, accessing Kubernetes. And then we can do something like kube control, give us the services that are running, or give us the running pods. And this means this is currently empty. So what is that? A service or a pod? So how our application looks like in container orchestration is similar to follows. We're going to have, well, a pod and a so-called service. So what is that? A service is a logical abstraction over an application or over a microservice in our case. That means if we have a coffee shop application, the application itself, that would be a service that might be backed by multiple running instances. So if we want to have multiple running application servers or containers or runtimes that all provide the same functionality, that would be one service for the coffee shop implemented by multiple running pods. A pod is an atomic workload in Kubernetes. So that means we have one or more running pods, and each of them contain a container, a Docker container, for example. And this is provided by the coffee shop service. And now if we want to access and order some coffee, we're going to access that coffee shop service and end up at one running instance here. And then in the same way, if the running container, if our application wants to access another application, for example, the Barista, it accesses the service and ends up at one of the running pods, and, well, the same way back. So let me quickly show you some YAML code. Yay, everybody loves YAML. So this is modern way, I guess, how to define cloud native resources. We're going to have some YAML definitions for a service and a deployment. Well, now, hold on. What is a deployment? Well, a deployment is a way how to manage pods in a more sophisticated way. So, for example, if we say we have a running instance, a running container, and now we want to actually deploy a new version or scale up or down, that means we, instead of creating a pod directly, we actually create a resource that manages pods for us. And this is the deployment. And we can say, now please provide one replica, one pod of the following specification, for example, with the following Docker image that we just built, and run that. And what is up here is the service definition. So this is just defining a name, coffee shop, that's the name of the service. And it's going to forward, well, the port 9080, that's the default port for OpenLiberty, to the following pods that are, well, that contain this label, app coffee shop. So I might have multiple pods that back my coffee shop service, and that all, well, are selected then from the service. And the service does a load balancing or load distribution to all the running instances there. All right, the Barista one looks very similar. We have a Barista service here with a name, Barista, and also, of course, a deployment. These two applications, again, are totally isolated. All right, now let's do this. Let's finally deploy something. We're gonna use kubecontrol apply command to, well, apply these resources that we have. So we're gonna, we can throw in a whole folder, actually, of the coffee shop and the Barista, and then it's gonna create all the resources for us. The reason why this is called applied, and this is actually a nice story, we can say, oh, if I reapply that, it actually doesn't hurt anything. These resources are applied or changed or created depending on the current status of the cluster. So if that's already existent on the cluster, that doesn't matter. And now if I ask for the services that are in my cluster, kubecontrol get services, I'll see a coffee shop and a Barista service, and kubecontrol get pods give me, well, gives me the running pods. One for coffee shop and for Barista. All right, that's nice. So now we're going to access that. And I get my cluster IP in my running cluster. I say coffee shop resources orders, for example. That gives me the coffee orders that is, well, empty JSON array, because there are no orders in the system. So this corresponds to what you just saw in the orders resource. This is now deployed. Here, that is the coffee shop application I accessed. Well, the IP of the cluster, coffee shop, that is the context path of my application. Then resources is actually, well, the name of my JAX-RS application here. And then we end up at the orders resource. All right, and we get the orders and the system. That's in memory, actually, for default, for example cases. So there's nothing here. There's no coffee yet, but let's change this. We're going to create some coffee. So that means I need to post some JSON to this resource, right? Going to create a post request using curl, for example, where we're going to post some application JSON content type. Let's have a look at how the coffee order actually looks like. The coffee order has a bunch of things, and especially a coffee type that we want to provide. That means, well, espresso or latte or whatever we want to drink. Let's say we would like to have an espresso here. And we're going to create that, and hopefully, well, that works. 201 created. So that has been created. And hopefully, well, yeah, that's already also in the system. All right, that's good news. So apparently we now have some coffee in our system, some coffee order at least. All right, so one thing that you might have noticed if you look at how the Barista service is being accessed in our coffee shop application. If you paid attention in our HTTP client, how we connect it to the other application, that's already very interesting, is we did not configure any IP address or any DNS resolution, something like that, for the individual environments that we might have. We only specified Barista, which is actually a very nice story for us, because this enables us to, well, hard code even that URL and to get rid of environment-specific configuration. So how does that work? Kubernetes per default does, where is my resource? Does a DNS resolution, a cluster internal DNS resolution for all the service names. So that means because of that name Barista, we can actually access Barista, do a hostname lookup in that internally in that namespace in the cluster, and end up at one of the running instances of our Barista application, which is very nice because then we don't have to configure an IP address or a DNS name for example, test system.barista.example corporation and so on and so forth. So this makes it very easy for us to get rid of configuration here. So that's about the Kubernetes here. And then apparently, well, that works. So as we saw, this already gives us that running application in, well, production, in a production setting. So a few more things when it comes to configuration, for example. And configuration is a very interesting part, especially if we talk about, well, 12-factor applications. So 12 factors are, well, interesting aspects that have been set up in this initiative here that you might have a look at. And especially if we build our enterprise applications using, well, cloud-native technologies, using containers and container orchestration, you might have a look that pretty much all of these factors are then already applied. For example, configuration. That means get rid of the configuration on the application level and rather try to inject it from outside of the application, from the environment. That means we don't want to configure which Barista backend application we use. Well, we make that part of the environment by using a DNS resolution. Or in other words, if we have to change our application, if for some reason it has to behave differently in different environments, then we do not want to build multiple running, multiple binaries, actually. No, we want to build one and the same binary once and provide it everywhere and, well, inject potential differences from the outside. Why? Because of reliability and because of testing. That means in our continuous delivery pipeline, we want to build our image and binary once and use that binary in each and every stage and test it. So then we can be sure that later on it will work because we always test the same thing. So this is one thing that I already use here in especially the my coffee shop class here. If you maybe saw it already, I have a location here that is actually being injected or being configured, that is, well, where my coffee is being brewed, I would say. So if we have our coffee order, and if, for example, we access that order here, then we might see, well, we have also a location available. The default, it's going to brew it on Java, so the island. So in this case, where does that come from? We can configure actually this brew location, and in this way, we're going to use MicroProfile config. So actually, if you use an application runtime that supports the Java EE or Jakarta EE standards, as well as MicroProfile projects, for example, MicroProfile config for configuration, you can actually use and mix and match all the APIs that are part of, well, Enterprise Java, that are part of Java EE/MicroProfile. So why do I want to use this? Well, I want to configure my application here in a somewhat cloud-native way. That means I don't want to change my application here, but provide the configuration from the outside. In this case, it's actually provided by an environment variable. Well, how do I know this? There are multiple default config sources in MicroProfile available. That means this lookup key location here might be injected from, for example, the environment variables of my running container, of my system. So that is being available out of the box, and then I can provide this location here. Per default, that's being called home, and I have a few locations available, and the lookup, well, per default is home, or unless it's provided, well, in an environment variable. So where does that come from specifically? In my deployment, you probably already saw that. Actually, I'm going to set an environment variable, location. So that is a Kubernetes specific configuration. It's very similar to a Docker run with an environment variable parameter. It actually does that under the hood and sets this environment variable, well, with a specific value. So you can either set a value directly, for example, Java, or say the value actually comes from a config map or another configuration store. So a config map is another type in Kubernetes where I can actually configure something in an environment. And then later on, what I actually want to achieve here is to say, well, in this running deployment, I want to configure it using that environment config map configuration, or I'm going to actually outsource this snippet, put it into a different file for a different environment, for my test environment, for a production environment, and I'm going to overwrite that using a different location. And then, well, I can reconfigure my application without actually changing the image. So this is very nice, and this, well, implements the 12 this approach of the 12 factors here. All right, that's about to say about the 12 factors. Now, if we have a look at that, this already runs in production, this example, but it's certainly not, well, production ready. For example, it's lacking a few concerns. And now this is where service meshes or Istio come into play. And especially if we think about, well, the part observability, what is going on inside our application, then we might not, well, see or know everything here. So that means just because our request has been created here, and just because our diagram says that apparently the Barista application is being called, we actually have no clue what's going on. We don't really see into the system. So we lack observability here. But thankfully, the cluster that I have here is not only a Kubernetes cluster, but is in fact an Istio cluster. And Istio is a service mesh technology that, well, is probably the most widely used service mesh technology out there, and it heavily builds upon Kubernetes or supports Kubernetes and works very well together. And what is a service mesh? Well, a service mesh is a mesh of interconnected microservice deployments where we actually can add some concerns to each and every application without changing the applications directly, but adding concerns from the outside in a somewhat transparent way. Concerns such as observability or resiliency or more advanced traffic management. And let's start with observability here. Actually, there is one way. Let's have a look at the Does that work again? My secret port forwarding so that this works. This is Grafana. What is Grafana? That is a monitoring technology, and I did not set that up. That is actually being provided and included in the Istio installation. So what we're going to have, we have some dashboards here that are actually available and that are already, well, activated for my services. So we have a coffee shop service here. Again, I did not configure that. That uses an auto discovery inside the technology. And now, I don't know about you, but I think we need some more coffee. So what I'm going to do, I'm going to create some new coffee, create some new coffee, create some more new coffee, new coffee, new coffee, new coffee, just to have some more traffic in our system. And now, well, I'm going to see a little bit more in my coffee shop. So I see that this coffee shop service actually has now some traffic. So it includes some default, some technical metrics out of the box. For example, what is the request volume? What is the request duration for that specific service? And when we look at the Barista service, we also see that we now actually have some traffic incoming into the system. And also we have a look at where the traffic is coming from, and we see, oh, it's actually coming from the coffee shop. So that means that the coffee shop is indeed calling our service, our Barista service. Okay, so that is being provided out of the box with Grafana, with monitoring. And another nice story that is being provided is, now that connection is failing. So what I'm going to do here, actually, I'm going to forward the port of specific, well, services into the cluster. So that's actually not running on local host, but that's running inside the cluster, and I'm just using a kube control, a port forward command. So what we have here is this cute little guy with the German name Jäger. That is a distributed tracing technology. And with that, we can trace individual requests that go through the system to, well, being able to backtrack what's actually going on and which request is going through which specific instance. So if you're going to have a look at that particular request, we're going to see that, well, this request is going into, well, the cluster to the ingress gateway, and it ends up at the coffee shop application. And then we have another request that synchronously calls our Barista application with, for example, a request that we already know. If we had a look at the code, HTTP put request to that URL. So now we see that this is actually being called, and we see that the coffee shop is actually calling that instance of the Barista service. So we can backtrack what's going on inside our system. Another interesting technology is this one that is called Kiali. Kiali is a service graph technology, plus a bunch of other things that actually knows about the Istio configuration. So it's aware of what's going on here. And let's have the fancy animation here. And what we see, we're going to see all the Istio resources here. For example, our coffee shop service and the Barista service. And, well, which one and which particular version, what that is, I'm going to explain in a second, is calling which. So this has a look at the actual requests that go through the system and builds up the dependency graph of our microservices, which, well, quite frankly, is pretty much boring since we only have two applications, so one calls the other. But if you can imagine, if we had a more complex setup here, then we actually see which version is calling which application. So now, how does that work? Especially that observability being provided out of the box. So in a service mesh technology, or in Istio specifically, what we have is we have our services, our Kubernetes services, and our deployments that are, well, running instances, running pods. But now what we do, instead of only having the main container, we actually have a second container, so-called sidecar container, a proxy container. And actually, if we call a service, for example, the coffee shop, our request actually ends up at the proxy container, and then will or might forward our request to the main container. And then if the main container, if our application wants to access another service, well, it accesses that also through the proxy, and that request ends up at another proxy that again forwards it to the main container of the Barista instance and the whole thing back. And these sidecar containers are deployed in each and every pod. If we had multiple pods, each and one of them would have its own proxy. So this is also why, if we have a look at the pods, you see that we actually have 2 containers in each and every pod. 2 are ready and they are running, and this is also being provided out of the box. I did not specify 2 containers, I only specified 1 each, but this is being injected by Istio. And now you can imagine, how all of that observability works, because, now the proxy sees all of the communication here and has the ability to emit that information. For example, to Prometheus and Grafana, or to Jaeger and Kiali, and so on and so forth. There is another thing to be done in Jakarta EE, or in our application actually, if we want to make that work. Because, if you have a look, or if you imagine how that distributed tracing technology works, specifically, how do we know, or how does Jaeger know that this request is somewhat correlated to these requests? Well, the answer it doesn't, because just because that request coincidentally happened at the same time as the other request, that doesn't mean that one caused the other. But what we have to do actually is to provide correlation IDs, typically in HTTP header information. And this is actually what we have to do manually. So Jaeger or Zipkin introduces a de facto standard, Open Zipkin or Open Tracing, where we had to pass HTTP headers. They're typically called X-B3-trace ID, span ID, and so on and so forth. You might have seen them before. When we need to pass them in our synchronous request, that actually goes through our application, because we have our orders resource here. And if we create a new coffee order, then we're going to end up at this resource, and then Istio injects these HTTP headers for us. But that means that now inside our application, we would need to take these HTTP headers, pass them here in the next call, pass them here into the HTTP client, pass them here, or actually pass them here, and then extract the HTTP header information again to, put that to the HTTP client, because that's a synchronous request, right? Well, that works, but this will be actually pretty cumbersome, so we don't want to do that. What we can do, luckily, is, use another project that is being provided by MicroProfile that is called MicroProfile Open Tracing. And now, if you have a look at my specific Maven project here, I don't even introduce that API. Why? I only used Java EE APIs plus MicroProfile config plus actually health check. This is due to the Kubernetes health checks that we're going to introduce, but not the MicroProfile Open Tracing. Why? Well, because we don't even use the API, but what we can do is to instruct our runtime, in this case OpenLiberty, to please provide this functionality to use the tracing headers and pass them out of the box automatically to any HTTP client. How does it work? So this is now Liberty specific. And what I'm doing here is I configured my running Liberty with these features that I can use. So this is now the little bit optimized version that is a little bit more verbose. I can say, okay, I use specifically these features here in my running runtime. So that is optimizing my runtime a little bit. And what is the interesting part here is actually these MicroProfile Open Tracing and, a Liberty specific Zipkin implementation of that. What does these things do? Well, these things actually enable me that if I get a request into the system that has these open tracing headers available, then, actually I can pass them here. And if I end up in a synchronous request in a HTTP client, in a JAX REST client, then it will automatically pass these headers in my request, and I don't have to do anything else. I just have to instruct the runtime that this is actually part of the application and this will work. And it works because, well, we see that this actually connects to the other and correlates to the other request. So this is shown in this particular one page. The one request causes the other. That's what we need to add for the tracing example here. Other than that, we can see that the service mesh, well, provides all this information. And then further, how that works is we're going to have, well, a control plane that consists of multiple components. So that's provided by the Istio installation. And that control plane actually communicates with all of the individual proxy containers. So then we can, well, configure all of the proxy containers, how they actually should behave. And also we can scrape all of the telemetry data to provide that observability. All right, that's to be said about the observability part. What else we can do in Istio actually is, well, to have some more advanced networking or some more traffic management. Because we have these proxy containers being available. So now we could actually say, well, instead of routing to this Barista instance, for some reason, route to something else, or provide some more resiliency here. So the proxy has now more control over this. So let's start with some more advanced traffic management. So this is a fun part. Let me quickly show you some Istio resources. This is now a lot of content here, and I will provide you some further resources where I can actually read and watch that in a little bit more than 1 hour. But just as an introduction, what we have in order to configure the traffic management in Istio is we have some more YAML. Yay. Especially some resources that very much look like Kubernetes resources. And actually, these are Kubernetes extensions. So one type is called virtual service, and another one is called destination rule. So what are these? A virtual service is, well, configures a service that is part of the service mesh with regards to traffic routing. So it configures the routing rules for, in this case, the Barista service. And what is a service in the service mesh? Well, per default, all of the Kubernetes services are actually Istio service mesh services as well. But also we could have some more advanced examples. For example, we could provide wildcard virtual services or extend our mesh with services that are not actually part of our Kubernetes cluster. That's why it's called virtual service. And we can provide some routing. In this case, all of the HTTP routes, everything that is routing to Barista host, please route to the Barista backend. So that's very boring. That's actually a default route here. And we have this destination rule that configures further policies for a specific destination, for our Barista's destination. For example, if we want to have some further authorization or some mutual TLS that we can also do in Istio, we could provide that here. And it also provides the subsets. So what is a subset? A subset is a further, well, subsetting of a specific service where we could divide a specific service to multiple, well, slightly different instances. So we have only one subset here that is actually called V1, and it selects all of these instances here by a specific label. You might have seen that before. This label is actually being provided in the pods. So this is another meta information to, well, select some information here. Out of the box, it doesn't do anything because we always route to that label, but we could specify that further. How the coffee shop looks like is very similar. We have a virtual service and a destination rule as well. And since that is also the user-facing application, we have something that is called gateway. If you're familiar with Kubernetes ingresses, this is actually very similar. This provides the ingress traffic into the service mesh. Why we use a gateway? Well, because this is aware of the Istio configuration here, and this then already can use the correct resources and proxies here. And we're going to route, well, also everything to the V1 subset. All right. Now, if we want to have a little bit of a further configuration here, what we could do actually is, well, provide another subset just for fun that we call v2. Now let's live code some YAML. Let's be brave here and hope that works. Actually, I now enhanced my subset of the coffee shop service to include v2 as well. You might have seen that before. I actually have a v2 example here that, well, uses a different tag, a different image here that works slightly differently. And what we could do, well, for example, we could switch that traffic to use the v2 subset instead of the v1 subset. So what we can do here, we could apply this now. The nice story about that is, since these resources extend Kubernetes, the Istio resources, what you can see here, we can actually use kube control to, well, use the same resources in the same look and feel. So for example, kube control get services gives us the services, and kube control get virtual services gives us these virtual services. This does not work in a standalone Kubernetes cluster, but it works once we install Istio because it extends our API, so we can use the same look and feel, which is very nice for the development or user experience. And now, if we ask for the coffee orders again, now this is actually empty. Why? Well, now because we use the other application, and per default, we don't have any orders in the system. So let's change this. We create another coffee order, and now we actually see that the routing goes to a different application, to a v2 application that, well, has a different response here. So we introduce some hypermedia link instead of just the ID, if you remember it from before. So this is now to reroute the traffic from subset v1 to v2, but manually or explicitly, not only done by Kubernetes deployment, what we could do also. So for example, what we can do here is to provide some more, well, advanced scenarios. So instead of having one destination, we might say, well, we want to have two destinations. v1 with maybe 70% of the traffic, and v2 with 30% of the traffic. So this is how we could implement some A/B testing, for example. That means we deploy two specific versions of our application, and now we instruct the Istio proxies actually to, well, do a split traffic routing with a percentage-based routing here. So if we say, let's do this again, or not only create it, but let's ask for the coffee orders. So either we get, well, the full response with all of the orders being created before, or, well, this response with our new application, with the v2 application. So this is how we could implement A/B testing here and canary releases. So for example, if we have a new version and we only want to route a specific subset of our users to introduce a change, not in a big bang way, but for example, introduce only 5% of the traffic first, or then 30, and so on and so forth, and gradually increase that, this helps us a lot in doing so. And we can do that here actually in an automated way. So what else is there? We could have some other approach where we do some A/B testing as well, where we said, okay, instead of that, we actually introduce some further criteria. For example, saying instead of the route match the traffic, for example, match the HTTP headers to, I think this is an array, to, for example, take the header header, I think it's name user agent. No, it's headers. Oh no, headers user agent. That's name, and then having a regex, for example. I think this is the default example to route the Firefox here, Firefox browser, to this route v2 and the rest goes to v1. I hope this routing was correct. Again, this is a YAML live coding. Oh, this was not correct. The error headers user agent. Is this correct? Nope. So this is why you should not do live coding with YAML, I guess. Now I need to actually have a look at how that looks like. User agent match and route. Oh, this was correct. Yeah, the first one is an array, second one isn't. Again, live coding. But now what we can see that if we ask for our coffee orders, then now we always get the version v1 unless we specify, in this case, an HTTP header, user agent, or, well, we actually use the Firefox browser, and then we only get this resource. So this is, again, for further A/B testing to route a specific subset of your users to that resource, for example. So let's undo this. Again, let's route everything to v1 again and apply it. So this is how to introduce some further advanced traffic management. What I also include here and will provide you as some code is actually some example where we can do canary release with a more automated approach. So what you should do, of course, as part of your continuous deployment pipeline or as part of your deployment setup is not do that in a manual way like I just did by manually editing YAML, but actually to provide some automation where you make this part of your deployment to say, okay, we have a new deployment here. That means we have a new version of Coffee Shop or Barista, for example, and how we deploy that is not in a big bang approach, but in order to set up a new version of Barista and use Istio to gradually increase the traffic routing from, let's say, 1% to 5% to 25% to whatever you want to specify, and then use also the provided monitoring to see whether the new version immediately blows up and produces a lot of errors, and then automatically roll back if that's the case. Or you can roll out further and increase that traffic to, well, not affect that many users if something goes wrong, to have a better automated approach of your deployment. So that is an approach that you should take. What I told you before is that we also have some resiliency being built in. So what we can do actually is to say, well, what happens if the Barista's service actually goes down and becomes unavailable? How does our application react if that is not there? So if you had a look at the Barista HTTP client here, is that, well, we use the HTTP client with a timeout, which is always a good idea. So we specify that timeout behavior here. But what if we were using some technology where that is not the case? Or what if, well, that is not supported or being specified? Well, actually, in this case, we can also use some, for example, timeout behavior in our proxies by the Istio configuration. So what we can do actually is to provide, well, a timeout definition, for example, with 1 second. That is part of this route here. And that is being provided in our virtual service routing. So if we apply that, well, this means then, well, we have a timeout being applied. And now if we, well, create our coffee orders, that is guarded by a timeout, I guess. Well, does it work? I guess. It looks like it, right? Well, how do we test it, whether that timeout is actually being applied? Because that route now is guarded by a 1 second timeout. So that means if that would take longer, or if the Barista application is unavailable, then this will kill the connection after 1 second. But in order to test it, we would either need to redeploy a fault test version of our Barista application in order to test it, whether that works, right? Always test whether that is actually the case. Or we use, well, some behavior by some functionality by Istio that actually can do that. So for testing purposes, we can actually introduce some faults. So that means, just for fun, we can actually instruct the Barista service to, well, throw some errors or make the connection slower. So what we can do is actually to introduce some faults. For example, some delay. Let's say we want to have a fixed delay of 3 seconds, but not all the time and only in 50% of the cases. So now, for testing purposes, don't do that in production. This will make the application slower in order to test the behavior of, well, of our application or of, well, the environment here. So what happens is that now either that request immediately works, or the Barista application, since that is being called in a synchronous way, would take 3 seconds, which is actually too long for the timeout, and then we get a timeout after, well, 1 second. That is being provided here. And then we also see, well, that we have a fault request. If we have a look at our, let's try to find a faulty request here in our distributed tracing with the Jaeger, for example. So I kind of find one right now, depending on how much we trace here. So that would be visible here. If we had a look at one particular request that is actually being aborted after 1 second, or where we also see it. So this is now actually more interesting. The Kiali observability, the service graph, now provides us some more details. So before we had V1 and V2. So that is now available since it knows about the subsets, and it would show, well, where we're routing to. And before we were actually routing to both versions. Now we only route to V1, but we see that this is not, well, fully functional, that we get a specific error rate here calculated over the last time. So that again provides some more observability, what's going on here. Same with Grafana, what we see in the coffee shop application, the success rate goes down, and so on and so forth. So that provides you some information out of the box. So this is also helpful for debugging and testing purposes in general. If you want to test how your application reacts once an external system is faulty, then you can have a look at that as well. What is also very helpful, so just quickly, the last thing is, well, how to debug your Java Enterprise applications in a Kubernetes environment. So there are a few tools available that actually help you, well, to debug what's going on here. And specifically what I want to show you is 2 things. Is one tool called Watch and Deploy, or WAD, made by Adam Bean, which, well, does not much. It actually listens for any file changes and rebuilds and redeploys your application into a thin deployment artifact. Same thing what we have here. And what you can also do, well, if you point WAD to a deployment directory that is actually being connected to a running container, you can hard redeploy your Docker containers as well, not just local applications. Well, but now we also have Kubernetes. So that works. I provided some information if you want to look at have a look at that, how that works with local Docker containers by using WAD. But it also works, well, using a Kubernetes cluster if you use a tool called telepresence. So that is a tool to, well, connect and replace containers that run in a Kubernetes environment with your local processes or local running containers. So what that is, it, well, introduces a two-way proxy where you're actually providing an instance for a running service, such as coffee shop, where you then, well, actually provide that service with something that runs on your local laptop. Just for testing purposes, you can connect into the cluster and use the same, well, networking features, for example, the DNS resolution that I showed you before. And if you use such a tool, such as this watch and deploy tool, you can even hot reload your code, have code changes here, and have them being reflected in your application. So for example, if we provide this orders example again, we have the coffee orders here. Well, now we have the timeout example, so that takes too long. But now we see, okay, new application, no orders in the system. And what is now here is that this is actually being replaced. And then locally, we have, well, a running coffee shop container. And if we access our application here, we actually end up at our local running container. And what we can do then is actually change something in our application. For example, say, well, instead of just providing the order here, also provide some, let's say, the location that I just showed you before. So we want to enhance this to introduce the location into our order as well. And now what that is doing is actually rebuilding our application and then immediately redeploying. And especially if you use an application server that can redeploy quickly, that means your changes are automatically reflected. Okay, well, now you don't see anything because we have to create an order first, but then you see, well, now also in the orders resource, this location is being provided, location Java. And again, we could change and redeploy it or introduce some other examples, and immediately you would have your change available that is actually only in your running Docker container locally, but very quickly, as you see, it very quickly redeploys. And if you use a tool such as telepresence, you can actually connect that into your local development, to your local Kubernetes cluster for development purposes and to debug or develop your applications, connect into them, and well, debug them locally in the local container if you need to, or use such a tool to improve your development productivity. So that's another way to well introduce some further productivity enhancement for your Jakarta EE application inside a Kubernetes environment. So a few takeaways for container orchestration or Kubernetes in general. What it provides us is, well, a few things. For example, we have some service discovery provided. We saw that in the Barista application. We have some DNS resolution being there out of the box. And the services specifically distribute our load and do some load balancing over the multiple instances we might specify. And of course, Kubernetes also sets up all the complicated networking and configuration of our application, so we don't have to do that in our application. Also, we have some deployment and scalability options. We can deploy a new version with zero downtime. We can scale up and down, having 1 replica, 2 replicas, 10, in a very simple way, in a declarative approach. What service meshes provide is they further than that add some cross-cutting concerns to our services in a transparent way. That means without changing our applications. So concerns such as resiliency, traffic management, observability, authentication, authorization, and so on and so forth. And specifically, what I like about it is it integrates very well with the approach of Java Enterprise, so that we don't have to, well, put in all these concerns into our applications or into the implementations. So what we ship actually is still a thin deployment artifact that, well, builds and integrates very well with containers, with Docker containers, thanks to copy and write file system layers. And that means our business logic is being provided in the application, in the Java code, using the Java EE and Jakarta EE APIs. And everything else is then, well, either being implemented by the application runtime, by the application container here, or being part of the environment. In this case, then, the Istio cluster and the Istio sidecar containers. So by doing so, we can actually focus on what we should focus on as developers, that is implementing business logic. So now, if you want some further resources, what I have, you have this example available on GitHub with all the code here, including some workshop actually that we created where you can go and get your Kubernetes cluster with Istio in the cloud. So you can get that for free and try out Kubernetes and Istio if you want. We have a lot of resources available here where you can see coffee shop, barista service, create your own coffee, and also, well, see the observability features of Istio, see how that integrates with Java EE, Jakarta EE, and MicroProfile, and have a look at that if you want. So I will provide you all of these links and also how to do this WAD, watch, and deploy approach with Docker and with the Kubernetes debug example. Other than that, I hope this was a very helpful session for you, and thanks a lot for your attention.
Thanks so much, Sebastian, for an awesome demo, and thank you to the community for coming out and watching. It was fantastic. So as Sebastian said, he'll be providing links. I'll throw them in the description down below for everybody to access. And at this time, we have no questions. So thank you for joining us, and we'll see you for our next Jakarta EE Tech Talk. Have a good one, everyone.
Thank you.